Hello. So, we are discussing goodness of fit test, and we have already discussed the Pearson goodness of fit test, which was a chi-square test indeed. And this lecture we are going to uncover one more goodness of fit test. I would rather say this goodness of fit test is widely celebrated as well as widely used test in the context of any kind of statistical analysis. So, today's lecture will be started by one sample Kolmogorov-Smirnov test. So, let us have a quick background of this Kolmogorov-Smirnov goodness of fit test. In chi-square goodness of fit test, what you have done, you have made all the observations classified into k categories. Okay. So, the comparison between the observed and the expected frequencies is made for a set of k groups. Remember it? So, if your total number of observations are small n, then k must be less than equal to n. That means the number of classes must be less than equal to the number of observations. That means we are losing information somewhere just by classifying the observations into some groups. Also, we have seen that for continuous variable as opposed to discrete or categorical values, grouping can be done in non-unique way, which leads to non-unique chi-square value, right? So, what would be the way out? An alternative way out of these a traditional chi-square goodness of fit test is to construct a goodness of fit statistic based on the function of the deviations between the empirical distribution function and the population cumulative distribution function specified under the null hypothesis. So, first and foremost, one idea or one question triggers in our mind that what is the empirical distribution function. An empirical distribution function, in short ECDF, is the distribution function associated with the empirical measure of a sample. This is an estimate of the population CDF. Empirical CDF is a step function that jumps up by 1 by n at each of the n data points. So, that is all about the definition of empirical distribution function. But mathematically, how do you calculate empirical distribution function? So, suppose you have a data set x order 1, x order 2 and x order n. These are the ordered sample observations, and you know what is meant by ordered sample. That means you have to arrange the samples from the lowermost value to the largest value, right? So, then empirical CDF is FNT, which is number of observations less than equal to t. So, you are fixing one value t, and you are just counting out how many observations in your sample is really falling less or equal to that value t divided by n, because it is a probability distribution function. So, FNT must lie within 0 to 1. For example, take a sample 12, 11, minus 2, 0, 9 and 5. So, what is your total sample size? That is n is equal to 6. First, arrange the sample observations in increasing order. So, the lowermost value is minus 2, which is followed by 0, then 5, then 9, then 11 and 12. And empirical distribution function Fn minus 2, that means how many observations are less than equal to minus 2 divided by 6. So, just count it out, how many observations in this sequence is really less equal to minus 2, only one observation, that is minus 2 itself. So, 1 by 6. Similarly, how many observations are less than equal to 0? So, count it out, minus 2 and 0. So, 2 observations. So, 2 by 6. Clear? Similarly, you can find out the empirical distribution function for x is equal to 5, x is equal to 9, x is equal to 11 and x is equal to 12. Now, one quick question of interest might come into your mind. Suppose I am fixing t as 1. Now, you will see in this sequel no 1 is there. The values are -2, 0, 5, 9, 11, 12. So, 1 is not there. So, what if I ask what is fn 1, then what will be your answer? The technique remains the same. How many observations right from these bunch of sample observations are less than equal to 1? So, there are two observations, one is -2, another is 0, both of them are less equal to 1, means less 1, equality does not happen here. So, fn 1 for one value, the empirical distribution function happens to be 2 by 6, clear? So, that is how you can figure out the empirical cumulative distribution function. Now, as I was saying, empirical CDF plot looks like a step diagram gradually going up to 1. Take the previous example, that is the 12, 11, -2, 0, 9, 5 example. In R code, you can always draw the empirical distribution function just by using the comment ECDF. So, if x is this, then ECDF of x, that is your empirical cumulative distribution function of x, which just now we have done manually, of course, but R will do it on your own, and by using this syntax ECDF, and then by using the function plot ECDF x, you can have the picture like this. You can see that picture is almost like a staircase, okay? And the jump, suppose we are sticking to this part, and the jump from this stair, this step to the next step is 1 by n. Since we are dealing with 6 observation, so this jump is 1 by 6, okay? So, like this. So, that is why it is said, or it is taken as an estimate of the population cumulative distribution function. Suppose there are 20 observations from normal 0, 1. If I ask you, draw the empirical CDF and the true CDF. Why true CDF is coming into the picture? Because I have already mentioned the distribution function as the distribution function of standard normal, right? So, what you will do, you have R at your own calls. So, open your R studio and you will extract out, generate 20 observation from standard normal 0, 1, plot ECDF x. So, that will give you the stepwise plot, and if you want to have an overlay with the empirical cumulative distribution function and the true distribution function, then you have to use curve P norm x, means the x observation which you have generated earlier, mean is equal to 0 and SD is equal to 1, and col means the color for this curve we are going to have red, and a very essential argument which you cannot ignore at all, to have the overlay picture, means two graph will be imposing each other, two graphs on a same plot, okay? So, that is what is done by this argument add is equal to true. So, if you do like that, you will have this picture, and the continuous one as well as the red one is the true CDF, and the step diagrams is the empirical CDF. Now, you can see how the true CDF differs from empirical distribution function. Since we have extracted observations from standard normal, so it is expected that the true CDF, that means the red curve, will go neck by neck with the step diagrams. Kolmogorov-Smirnov one sample goodness of fit test actually is based on these idea that how far empirical CDF is going from the true CDF. For testing the distribution function is equal to f0x. So, f0x is a known distribution which has to be completely known. For each x against the two-sided alternative, one sample Kolmogorov-Smirnov test statistic is dn maximum, and this maximum is going to be taken over the real line of real domain of x minus infinity to plus infinity. So, maximum distance, maximum discrepancy between the empirical distribution function and the true distribution function. As long as f0x is continuous, the probability distribution of dn does not depend on f0x. That is why one sample Kolmogorov-Smirnov or KS in short statistic is distribution free statistic. If empirical CDF, which is coming from the sample at your hand, is closed to the true distribution function under the null hypothesis f0, then the value of dn will be smaller. Quite clear. Just now we have seen in the context of the normal example that if your observations are coming from the distribution under the null hypothesis, then of course the empirical CDF will go by neck with the true CDF value, right? And obviously the difference between Fn and F0 will be smaller, and we are taking the maximum difference. So, it is expected that the maximum difference is also be very small. On the contrary, H0 is rejected if and only if observed value of dn for the given sample exceeds the upper alpha point of dn. Now, these upper alpha point of dn, these can be found in the Kolmogorov-Smirnov table. Remember, K's test is more powerful than the traditional chi-square test. Now, intuitively, why we are saying that it is more powerful? Of course, by mathematical tools and techniques, it can be shown, but look at your intuition, why this empirical CDF method is more powerful than the grouping method? Because in case test construction, we are using each and every sample point, and we are trying to investigate how far that cumulative distribution function is going from that same point empirical distribution function. So, basically in KS test we are using all of the points, which we are not when dealing with chi-square test, right? So, this is the table of the Kolmogorov-Smirnov test critical values. So, here you will see that at the extreme left all of the sample sizes are given, and at the top you will have that alpha, means level of significance, is given. So, if we are interested in alpha as 5%, we have to look at this column, and if you are interested alpha as 1%, then we have to look at this column. So, these are the tabular value. You have to make the judgment on the basis of this tabular value. So, you reject the null hypothesis if your calculated value supersede these tabular value for a fixed alpha and n. So, that is the common rejection rule. Now, let us get to few examples, because solving example will give you a better transparency related to the KS test construction. 10 observations are collected from a continuous distribution. Check that if they are from uniform 0 1. So, uniform distribution 0 1, the observations are like this 0.11, 0.32, 0.51, so on and so forth. So, what is our null hypothesis? Our null hypothesis is f is equal to f0, and what is our alternative hypothesis? Since it is a goodness of fit test, already I told you, for goodness of fit test your alternative hypothesis is always two sided, right. So, we will have to write f not equal to f0. So, you can write here f0 x, f x is equal to f0 x, nothing wrong in it, or in short you can write as f is equal to f0. So, what is the distribution function of uniform distribution, where the ranges of uniform distribution is 0, the lowermost range is 0 and the uppermost range is 1. Right from the statistical knowledge, it can be said that the distribution function is x, the density function is 1, and thereafter the distribution function for uniform 0 1 is x, where x lies within 0 to 1. Now, let us arrange the observations increasingly, because I told you when you are trying to construct the empirical CDF, you have to have the observation in a monotonic pattern, right. That means in an increasing pattern. So, the lowermost observation out of this entire bunch of observation comes as 0.11, followed by 0.32, so on and so forth, and finally 0.69. So, finding empirical distribution function for each of the point is pretty easy. You can just figure out how many observations are less equal to 0.11, clear cut. Only one observation is there in this given sample. So, that is 1 by 10, so 0.1. How many observations are less equal to 0.32? How many observations are there? Okay, just count it out, only 2 observations. So, that will be 2 by 10 and finally 3 by 10, then 4 by 10 and finally you will have 1. How many observations are less equal to 0.69? All the observations present in that data sets are less equal to 0.69. So, of course, empirical CDF will be 10 by 10 and 1. Now, for each of the observation, figure out the true cumulative distribution function. So, what is true cumulative distribution function? We have already deduced that the true cumulative distribution function for uniform 0 1 is only x, clear. So, x means if it is 0.11, f0 x will be 0.11. Similarly, if your x is 0.32, f0 x will be 0.32. 0.44, 0.44. It's pretty easy while you are dealing with uniform 0 1. Now, find out the distance. Of course, the absolute distance means no negative, no positive, the absolute distance, okay, modulus of the difference we need to take, and 0.11, then for 0.11 fn x is 0.1, and for 0.11 f0 x is 0.11. So, just difference 0.1 minus 0.11 and that is 0.01. Similarly, what is 0.2 minus 0.32? Take the absolute figure and that is 0.12, clear. So, you will have to figure out all of the absolute differences. Which one is the maximum differences? Just have a quick glance over this sequel and you could figure out the last entry, that is 0.31, is the maximum distance between the empirical CDF and the original or true cumulative distribution function. Now, just get to the Kolmogorov's-Smirnov table, which I have already shown you. For n is equal to 10 and alpha is equal to 0.05, the tabular value of dn is 0.410. We reject the null hypothesis if these calculated dn, which we have done here, is greater than d tabular, and what we can see here, we have figured out the maximum calculated distance is 0.31 and 0.31 is less than 0.41, which is the tabular value. That means we failed to reject the null hypothesis. What was our null hypothesis? The observations are coming from uniform 0, 1. So, well, we stick to this decision. Observations are coming from 0, 1, uniform 0, 1. Clear? So, for Kolmogorov-Smirnov test, one has to know the expression of the distribution function. If f0 is normal distribution, then we have to find out the distribution function of normal distribution. Sometimes manual calculation of the distribution function at x is difficult. So, sometimes you might not have the distribution function as easy as the uniform distribution, right. So, there you need to take the help from R code. Suppose we are dealing with the previous problem, how to solve it in R. So, the command which you need to employ here is just ks.test. You see ks.test, and the arguments are x, comma, that is what you need to incorporate. That is, your empirical CDF is going to be checked with which distribution. In that example, in that problem, we are making the comparison with the uniform distribution. So, you will have to write P uniform. P uniform means that is probability x less than equal to small x. So, P unif means this is the distribution function of uniform distribution. Okay? This is the f x. Clear? So, ks dot test, it will give you the value of d as 0.31, and p value, look at the p value. I already taught you that stick to the value of p value, because by looking at p value you will able to reject or accept your null hypothesis, that equal to 0.2374, which is quite bigger than 0.05. So, we fail to reject the null hypothesis. Exactly the same decision we happens to achieved while doing the same problem manually, right. One more problem that is also from uniform, but look at the range of uniform distribution, that is now -1 to +1. Perform Ks test to check on the goodness of fit of these observations. So, first you are extracting out the observations, and then you are asked to check it on the basis of Kolmogorov-Smirnov test. So, how to write? Y is equal to R unif. R unif means the random number generated from a uniform distribution. How many random numbers you need to generate? 50 random numbers. So, that is your first argument. What is the lower level or lower boundary of this uniform distribution? That is -1. And what is your upper boundary of the distribution function? That is +1. So, you have to write -1 +1. Now, Ks dot test, that is the Kolmogorov-Smirnov syntax, y comma P unif. I told you what is the role of P unif, and do not forget to mention the range of the uniform distribution, that is -1 and +1. Okay, -1 to 1, this is just 1. So, what is the value of D? Value comes as 0.15768 and P value is 0.1493. Okay. So, on the basis of P value, one can claim that null hypothesis is accepted. One more problem, that is a problem for normal distribution. You can see a random sample of 12 persons are interviewed to estimate median annual gross income in a certain economically depressed town. Use the most appropriate test for the null hypothesis that income data are standard normal distributed. So, these are the observations. what you need to remember, the rest remains the same. First, you have to incorporate the data. Already you know how to incorporate the data, clear. Second, since this is a non-standard normal, but your null hypothesis is the data are coming from standard normal distribution. So, you have to make these observations into the standardized format. So, your null hypothesis is x follows normal 0 1. That where people just may commit a error. So, what is that? Do not forget to look at your question. If your question asks that the observations are coming from standard normal distribution, then you have to make the standardization of the observations given here. That is what we have done here. Z1 x minus mean of x means x bar divided by standard deviation of x. So, Z1 are the standardized observations, and finally, you can just put on Ks dot test and Z1 P norm, because we need to check, we need to compare with the distribution function of the standard normal, and P norm is the distribution function of standard normal. To be more safe, you can write the mean 0 and you can write the standard deviation 1. In fact, if you are asked to compare with a non-standard normal, then in the Ks dot test comment, you can replace 0 by the mean which is given in your question, by the standard deviation which is also given in your question, and look at the d value and the p value. You can make the decision accordingly. Example 4. Example 4 is a problem where you are asked to test the normal distribution, but look, the mean is given as well as the standard deviation 20. Okay. So, then you have to use Ks dot test. W is your sample observations, that means 90, 106, 109, 117, so on and so forth. Then W and the next argument will be as it is P norm, and mean you have to write like that, mean is equal to 150. Mean is an argument. So, writing mean means you are indicating mean, fine. So, standard deviation is equal to 20, and if you just run this code, you will give you the value of the Kolmogorov mean of test statistic, that is D, along with the p value. Okay. So, just try it on your own desktop or laptop and figure out the decision. One more problem which is a little different, because so far whatever we have done the problems related to the normal as well as a couple of problems from uniform distribution. But this problem is a little different, because here you need to tackle exponential distribution. Okay. So, what is the, just go through the problem. Now, what is the distribution density function of exponential distribution? That is given as lambda e power minus lambda x. So, lambda is the parameter of exponential distribution. Now, in this problem, value of lambda is given as 0.009, clear. What is the distribution function of this density function? Just by mathematical calculation, one can show that the distribution function of exponential distribution is 1 minus e power minus lambda x. Okay. Since lambda is given, it will make your work, make your exercise easier, you know. In case lambda is not given, then you have to estimate the lambda and you have to use that estimate as the figure of lambda, which is not required for this particular question, right. So, this is the observation, aim and Ks test first argument is your observation, that is aim, and the second argument, which is really needed to be looked on, PEXP. PEXP means the probability distribution function for exponential. Okay. So, PXP, and the third argument is the parameter which is involved in that distribution function. Okay. And what is the parameter? Only one parameter is involved in exponential distribution, and that is given as 0.009. So, you can just write 0.009, and the rest will be very easy as well as very prototypical, as we did for the earlier questions. In fact, in R there are comments available for well known distributions. So, nothing to be worried of in case you do not know the distribution function. Okay. Mostly all of the well known distribution functions are jotted down in R as a R code, like normal, gamma, beta, binomial, Poisson, Cauchy, even double exponential, means the Laplace distribution in other terms. The common syntax from random number generation, say for gamma distribution, it will be R gamma, and how many random number you need to generate, that will come as your first argument. Then n, n means the parameter of the gamma, the first parameter, and the scale parameter, in case that gamma is not standard, then the scale parameter involved in R gamma, that you have to mention here. For finding probability, remember that R gamma is the random number generation. For finding probability or cumulative distribution function, we will use the syntax P gamma. Okay, already we have used. So, P gamma, up to which point you are calculating out the probability, that is x, and your parameters for gamma, there are two parameters, one is n and another is the scale parameter. So, you have to write the value. So, suppose n is 5, so you have to write 5. Suppose scale parameter is say 0.9, then you have to write 0.9 here. Similarly, for beta distribution, it is R beta, R binomial, R Poisson or R Poise, R Laplace, R norm. Similarly, P beta, P binom, P Poise, P Laplace, etc. You can find the list, the complete list, in the comprehensive R archive network. You will figure all these archival records in this website cran.r-project.org. So, that is all about the Kolmogorov-Smirnov one sample goodness of fit test, and I am pretty sure that once you are fine with Kolmogorov-Smirnov goodness of fit test, then you will not go for the traditional chi-square goodness of fit test, because Kolmogorov-Smirnov goodness of fit test uses all the observation, as I have already stated. So, try out on your own and get me back with your feedback. Thank you.